All right. Um, Hello. Welcome to the natHACKS 2024 workshop, Intro to BrainFlow. We're going to be talking about what BrainFlow is and how you can use it in your natHACKS project. If you're doing any project with any biosignal device or specifically EEG headsets. Um, so just first off, quick bit about me. My name is Harrison Fa. I'm a computing science master's student here at the University of Alberta. My research mainly focuses on using machine learning with clinical data to solve problems related to Alzheimer's disease, but I have also worked on other neurotechnology projects involving both fMRI data and EEG data, in which I have used BrainFlow for the EEG projects. Um, Also, throughout this workshop, I'm going to be bouncing back and forth between my slides and this code notebook, which has some Python code and examples of how to use BrainFlow. So if you want to follow along or just have that downloaded, you can go to nathacks.ca/ws2. And then if we just open that up, that'll just redirect you to a link where you can either download this code, or if you click this Open with Google Collaboratory, you can just run it just through Google Colab. I do suggest, however, running it through Jupyter Notebook if you have it, because then you can actually use the EEG devices to run the code. Whereas if you're running it on Google Colab, you're only able to use the synthetic EEG board. But it should still all run fine. It just won't be real EEG data to work with. All right. So just an overview of what we're going to be going over. So first off, I'm just going to talk about what BrainFlow is. Then I'm going to talk about how you can install BrainFlow. I'm going to specifically focus on Python, but as we'll see, there's many other languages that you can use BrainFlow with. Then I'll talk about how you can connect your hardware to BrainFlow. And then I'll talk about how you can read data from your device. And then finally, I'll talk about some of the pre-processing functions and other libraries that you can use with the data that you have read from your device. So first off, what is BrainFlow? BrainFlow is a package for reading data from EEG devices, but it also works with EMG, ECG, EOG, E blank G, pretty much any biosignal device, um, or not any biosignal device, but a lot of biosignal devices work with the BrainFlow library. And then it also contains functions for pre-processing that type of data. The benefit of using BrainFlow is that it is model agnostic and it has a wide range of supported biosignal devices. That means no matter which device you use, they're generally treated the same way by the BrainFlow library, which means you can sort of trade them out in your code without having to sort of start from scratch each time. Um, like I have done projects where I've directly um, tried to get data from the OpenBCI headset without using BrainFlow or any other library, and it's a pain. And it's a lot easier to just use something like BrainFlow. Another benefit is that it includes this a synthetic board, which gives you fake data that looks the same as if you were to get it from a real EEG device. Uh, that's useful for if you want to test your code, but you don't actually have an EEG headset or any other biosignal device with you. So if you're at home and you don't have access to your device, you can still work on the code and you can test it, and it should work just fine. Like, it won't be real data, but it'll look and have the same format as normal data. So for the BrainFlow library, you can find the documentation and examples at brainflow.readthedocs.io. Um, and it just has a bunch of information that we'll go over throughout the presentation. So BrainFlow is available in multiple different languages. So it's available in Python, C#, Java, MATLAB, and a bunch more languages. And the full list of languages with their installation instructions, API references, and code samples for each of the languages can be found on the BrainFlow site. So if we go back to that, so we have the installation instructions shows all the different languages that BrainFlow has support for. And then under the user API, it has API references for each of these languages. And then it also has code samples for each of these languages. And as mentioned before, it supports a wide range of devices. In particular for natHACKS, it has support for OpenBCI headsets, so the Cyton and the Ganglion headsets, and it also supports the Muse headsets. But again, there is a wide range of supported devices. If we go under supported boards here, we can see all the different types of biosignal devices that BrainFlow has support for. So how do we actually install BrainFlow? So installing BrainFlow is pretty easy, in particular for Python. So to install it for Python, you just need to have Python version 3 point something, so anything greater than Python version 3. Unless you installed Python before 2008, you should have Python version 3 and should be fine. And then if you have pip installed, you can just go into your terminal and type python-m pip install BrainFlow, and it should just install everything you need. Alongside BrainFlow, we're going to be using two other libraries. The first one is NumPy. So NumPy includes a bunch of different helpful functions for manipulating arrays or matrices. And by default, BrainFlow itself outputs all the data as NumPy arrays. So it's handy to have NumPy to be able to perform any operations on these. And you can install it similarly to BrainFlow, just using python-m pip install NumPy. And then we're also going to be using matplotlib, which is useful for just visualizing any data. And that can be installed with python-m pip install matplotlib. If we go over to the code notebook, just in the first section, I already have it set up to automatically install the libraries. So if you just run this section locally or even on Google Colab, oh, this is on Google Colab. If we come to here, sorry, and we run this section, it'll just automatically install BrainFlow, NumPy, and matplotlib. And then if you want to install BrainFlow in any other languages, you can come to the BrainFlow site, and under installation instructions, you can find how to install any other version of BrainFlow. All right, now let's talk about how to connect hardware to BrainFlow. So in order to connect your device to BrainFlow, you need to know two things. You need to know the board ID, which can be found on the BrainFlow site again. So if we go to the section where it says, if we go under User API and then Python API reference, if we look in this section, which has all the board IDs, you just want to find whatever device you're using and then just find the ID associated with that. So what I've got right now is I'm using a Muse 2. So if we scroll down until we find the Muse 2 board here, we can see that the board ID for Muse 2 is 38. Another thing that we need to know is the serial port for the device that we're using. So if you're on Windows, it's going to look something like COM3, COM4. If you're on Mac or Linux, it'll probably look something like /dev/tty USB and then a number. Now the serial port is a bit harder to find. If you're on Windows, what you can do is you can open your device manager, which I'm just going to demonstrate. And then if we go under View and then click Show Hidden Devices, and then I don't know if I can really zoom in, but if you go to the section called Ports, COM, and LPT, and open that up, we can see all the different serial ports that are connected. And so in my case, I know it's COM8 that my USB dongle is connected to. But what I can do is I can just unplug that, and then it refreshes, and then if I plug it back in, I can see that COM8 is now connected. So my Muse 2 is connected to serial port COM8. If you're on Mac OS or Linux, it's a little bit different. You have to go into your terminal, and then if you type ls/dev/period apostrophe or asterisk, sorry, it should list all the connected serial port devices. And I think if you follow a similar approach of just, unplugging and plugging in your serial port, you should be able to tell which one changed, and that will be the device that or the serial port that your device is connected to. All right, so I'm just going to show in the code how we can go about connecting our device to BrainFlow. Okay, so the BrainFlow, NumPy, and Matplotlib have installed in the background. Then I've got we're going to import these libraries. And the first thing that we have to do to connect our device is we have to define the serial port and the board ID that we found. So when you're creating like a BrainFlow board object, you feed in this BrainFlow input params object into it. That has, I guess if we go into the docs, yes. So the params object stores a bunch of information related to the devices that you're using. But the only one that is actually relevant in our case is the serial port. If you're using a device that connects over Wi-Fi or some other method, you might have to put in, the MAC address or IP address or whatnot. But in our case, they don't matter. We're not using them. We only have to change the serial port. So I've set the serial port to COM8. And then I've put the board ID to be 38, which is the Muse2 board ID. If you're using the synthetic device, it has, I think, if we pull up the board numbers again, if you want to use the synthetic device, you can just pass in the board ID as -1, and it doesn't matter what the serial port is. It should set it up as a synthetic device. So what we're going to do here is we're going to connect our device. So what we're doing here is we're passing in our board ID and our params object into this board shim object, which is going to be our device. And then we're going to prepare the session. So we're going to set up the device to be ready to record data. Now, at this point, when you try to call prepare session, if your board ID or serial port are incorrect, then it will throw an error. And in this code, I've handled that by, if the device doesn't connect properly, it instead sets the board ID to be that of the synthetic device. So it'll be -1. And then it creates a board just as a synthetic device. So if you're running it on Google Colab or you don't have a device, you can just run this code just fine, and it should create the synthetic board. So if I run this, oh, I gotta run this first. So we'll define those, and then we'll run this, and then it should connect just fine, hopefully, to the Muse. All right, it's still just running. If it connects properly, it'll say successfully prepared physical board like it did. Otherwise, it'll say device could not be found or is being used by another program. Because while if you have the incorrect board ID or serial port, it will throw an error. It can also throw an error if the board is being used by another program, or if you've got other code running in the background that's connected to it. It can only be connected to one program at a time. Or your device could be off, or your Bluetooth could be not working properly. There's a bunch of different reasons it could not work, but you'll have to troubleshoot that yourself. All right, so now that we've connected our device, we're going to learn how to read data from it. So there's a few things to know just before we start reading data from the device. So the EEG devices typically record samples at a mostly consistent frequency. I say mostly because sometimes you set your data to run for a second and it should have output a certain number of samples, let's say So the OpenBCI has a sampling frequency of 125 hertz, which means it outputs 125 samples per second. Sometimes you might run it for a second and it'll output 123 samples, let's say. Like it'll be close to that, but based on the way the buffer works, which we'll discuss a little bit later, it might not output the exact amount of samples. BrainFlow also records data in microvotes, which does come in handy later when we're trying to connect it to another library, which we will discuss sort of towards the end. And as mentioned earlier, BrainFlow not only records EEG data, but it also records other biosignal data. So we have to isolate the EEG channels because there are some devices that output multiple types of biosignals. So you have to specify what type of data you want to get from your device. So the way BrainFlow records the data is that while the data is streaming from the device, it stores samples in an internal buffer. And then you access those samples through BrainFlow functions. Some of the functions remove all the data from it when you grab the data, and some just copy the data from the buffer and leave it in. So you have to be careful and look at the documentation of what the function you're using is doing, because you don't want to sort of access the same samples over and over again and think that they're new data. Another thing we'll look into is inserting markers. So if you're recording data, you're doing some experiment, and at some point in the recording, you have like a stimulus, like let's say you have an EEG headset on, and then you're showing like a picture of a dog or a cat or something, and you want to know exactly where in the recording that happened. You can insert markers while you're recording the data. Like when the stimulus happens, and then afterwards when you save the data, you can go back and you can look at those markers. Okay, so let's jump over to the notebook and record some data. So this first section of code is just a basic example of reading data. So what we do is we first prepare the board. So typically, if you're using an EEG device and you're like reading data from it, you'll just prepare the board right at the start of the session, and then you'll release the board after you're done everything. But in this case, we're going to prepare and release the board in each of these code examples just so you can run them separately. So what we're going to do here is we're going to prepare the board. When we're then going to start the stream, so the board will actually start outputting samples. And then we're going to wait 5 seconds, and then we're going to grab the data. So we're just going to record 5 seconds of data and then save it. So I'll just put on the Muse headset, and then if I run this, you can see it's starting the stream, and then it should record 5 seconds of EEG signals from my brain. All right, now it's ending stream, and it should stop running soon. Okay, so it's done running. So it's saved the data in this data variable. So if we look at the type of this data and the shape of it, we can see that it does output as a NumPy array, and the shape of the array is 8 by 1248. So what this is we have 8 channels, and we have 1248 samples recorded from each channel. So I believe Muse records at 250 hertz. So in the 5 seconds, it should have recorded 1,250 samples, but it's 1,248, which again is what I mentioned earlier about it. It's not sort of exact, but it is close. Okay, and so now that we have the data, we want to specify which channels, we want to specify the EEG channels that we want the data from. So the Muse only actually has 4 EEG channels, but we can see that it output 8 channels instead. So those 4 other channels are for something else. I'm not exactly sure what they are, but if we call board.getEEG channels and then feed in the board ID, it'll tell us which of the channels in the device actually contain the EEG data. And then we're going to just grab, we're going to index the whole data array just using the EEG channel indices. So we can see that 1, 2, 3, and 4 are the EEG channels. And then if I just print the EEG data, we can see just sort of the general format of it. Depending on the device, you can also get other biosignals. So if I try to get the EOG channels, which is like eye recordings, we can try and print those out. However, the Muse does not support EOG, so it's going to throw an error. But if you had some device that supported EOG data, then it should output the EOG channels. We can also plot the data that was recorded so we can actually see it visually. So this is using the matplotlib library that we imported earlier. So if we output the data just from the first EEG channel, so there were 4 EEG channels, we're just going to get the data from the first one, and we're going to plot it over those 5 seconds. We can see this is what the data looked like. So again, it's all in microvolts. And then now we can record data and insert markers. So this code example is similar to the one we did above, except instead of just starting the stream and then waiting 5 seconds, we're going to start the stream, and then every second we're going to insert a marker. So after 1 second, we're going to insert marker 1. After 2 seconds, we're going to insert marker 2, and then we're going to do that for 5 seconds, and then we'll get the data. So we'll just let this run. So the way the markers work is that, oh, let's try that again. Okay, so now it's working. Okay, so we can see it's currently recording the data and inserting the markers each second, and now it's ending the stream, and then it'll save the data. So the way the markers work is the markers are saved in a channel similarly to how the EEG data is saved. So if we specify the EEG channels like we did before, and then we specify the marker channel, so we use board.getMarkerChannel, we can see that, as we saw before, channels 1, 2, 3, and 4 are the EEG channels, and then channel 7 is the marker channel. So the last channel of the 8 channels that get output is just for the markers. And then if we just grab all the markers from the data, we can see that it's a lot of zeros. So the way it works is for each sample, it prints out the marker associated with that sample. If we haven't inserted a marker, then by default, it's just 0. Whereas whatever sample happened right after we inserted the first marker, that will have a 1 somewhere in the data. And then after 2 seconds, there should be a 2 at the sample associated with the 2 marker. So what we can do is we can, if we get all the samples that have a non-zero value, we can get all the indices of the samples that have markers associated with them. So in this case, we'll just run this, and we can see that the first marker was placed at sample 227. We can see that the second marker was placed at sample 492, and so on. And what we can do is we can work backwards to try and figure out at what time the markers were inserted. So if everything sort of works smoothly and it had a constant frequency, then it should have the first marker output at 1 second, the next marker output at 2 seconds, and so on. But if we get the sampling rate of the board by calling board.getSamplingRate and then feeding in the board ID, we can see that Muse, for whatever reason, it says it has a frequency of 256. So that means each sample, it outputs 256 samples. Each second, it outputs 256 samples. And then we work backwards and divide the indices by the sampling rate. We can see that the first marker is apparently placed at 0.88 seconds. The next one is placed at 1.92 seconds, and so on. So it's not perfect. And this is why it's helpful to insert markers instead of just trying to assume, okay, we know the sampling rate is 256, therefore let's assume that after 1 second, the sample at 256 is when the stimulus happened. So that's why it's useful to place markers. One last thing we'll look at just for recording data is if you want to read data live. So in the previous samples, in the previous examples, we start our recording and then we wait 5 seconds and then we grab all the data we recorded in that 5 seconds and then we stop. If we wanted to save the data and let's say like plot out the data while we're still recording it, what we can do is instead of using the board.get data, which takes all the data, all the samples out of the buffer, what we can instead do is use board.get current board data. And then with this, we specify the number of samples that we want to grab. So in this case, instead of grabbing all the data that was in the buffer, it just copies the last 25 samples and leaves them in the buffer. So this is where you need to be a bit careful about how you're accessing the data, because let's say your board, like in our case, it outputs 256 samples per second. Let's say you're trying to grab data every second and you're grabbing more than 256 samples at a time. After a while, you're going to be grabbing data that you had already previously accessed because it's not being taken out of the buffer. So you have to be careful about making sure you're not grabbing data faster than it can be output if you want new data each time. So this example is similar to the one we saw earlier with placing markers, except instead of placing a marker every second, we're just going to grab the last 25 samples and output them. So if we run this, hopefully it runs fine. Okay. So we can see each second it's outputting the shape of the data. So again, it has 8 channels and then 25 samples for each of those 8 channels because we are specifying 25 samples. All right. I can take this off now. All right, so that's how you read data from the hardware. Now, the last thing we're just going to talk about is some of the pre-processing functions that BrainFlow has. So BrainFlow has a few different functions for ways you can process EEG and other time series data. So it has things like a low or high pass filter. So if you want to filter out frequencies above or below a certain threshold, you can do that. It has functions for downsampling. So let's say your model outputs data at 256 samples per second, but you kind of wanted it in a format of like 125 samples per second. You can use the downsampling function for that. And then there's also wavelet or FFT, which is fast Fourier transform functions, which are very useful for ways of processing and using EEG data, especially if you're using like a machine learning model. It's very handy to look at the frequencies involved in the signal rather than just looking at the raw patterns. But as was said earlier, the data is output in a NumPy format. So you're not limited to just BrainFlow because NumPy is a very common format for like arrays. So there's plenty of different libraries out there that have functions that can do similar things or more. So for example, the MNE library has many different useful functions for EEG, but that library, I believe, is not meant just for EEG, but for a wide range of different biosignals. So it might be beneficial to use that instead of BrainFlow once you've recorded your data. So if we go back to the notebook, I'm just going to show some examples of ways you can use these functions to process your data. So the first thing that I'll just mention, it's not a processing function, but if you want to save your data, Um, so I'll just show at the start, when we imported the BrainFlow functions, we from the data filter uh, side of BrainFlow, we imported data filter and filter types. So a lot of the pre-processing functions are kept under the data filter class. So we're just going to be using those. So if we want to save our data, we can save it as a CSV file by using datafilter.write_file, and then we feed in our EEG data and then the name of the file we want to save it as. And then we can also read that data back by using datafilter.readFile. And then lastly, I've just sort of subtracted the data that we had before and the data that we saved and then loaded back, just to show that um, while it's the same data that we saved and loaded back, they're not exactly the same. There's some sort of precision issues in how it can save the data. So they're like very similar, but they're not the exact same. So that's just something you might have to keep in mind if you're saving and loading data back. All right, so the first pre-processing function we'll talk about is low and high pass filtering. So what we'll do first is we'll just record some more EEG data to use. So this is just the same data. This is the same function from um, when we were inserting the markers after recording the data, but then I've also just grabbed the EEG data afterwards. All right, so it saved the data and then it should just put out a plot to show what the data looks like. All right, so this is what the data looks like completely unprocessed. And then now what we're going to do is we're going to perform a low pass filter, which removes, in our case, we're removing any frequencies that are above 50 hertz. And we're performing a high pass filter, which removes any frequencies below 2. So in this case, it's usually, especially with the EEG data, it's helpful to apply these filters. I can't remember the exact range. It's between maybe like 0 and 60 or something. But the brain only outputs at frequencies within a certain range. So if there's any frequencies outside of that, it's likely just noise and can be ignored or removed in this case. Um, so what we're doing here is we're performing these low pass and high pass filters, but we have to perform it on each channel separately. So for each of the EEG channels, we're just going to perform this uh, this filter, and then we'll plot it again afterwards. All right, so we've removed frequencies above 50 hertz and frequencies below 2 hertz, and we plotted afterwards. So looking at it, it's clearly done something to it. The data does look different, so I assume they worked. We can also apply the wavelet transform. So the wavelet transform is handy if you want to sort of know the exact frequencies that make up your signal. So in this case, for each channel, we're going to apply the wavelet transformation. And then we'll get the wavelet coefficients, which is usually what you're going to feed into your machine learning model, for example. And then we're going to just perform the inverse wavelet transform to try to get the original data back. And then I'll just plot the difference between the two. So we'll show that it, again, like saving and loading the data, it's not going to be exact, but it'll be close enough. Okay, so it runs very quick actually. But we can see there's very small differences between the data before and the data after we apply a wavelet and then apply the inverse wavelet. One thing to note with this though is depending on your version of BrainFlow, you might have to the parameters to these functions are a bit different. So I've had some versions of BrainFlow where you need to pass in a string for which kind of wavelet transformation you want to use. Whereas the version I'm using currently, if you pass in the string, it'll throw an error, and in that case, you have to pass in the integer for whatever wavelet transformation you want to perform is. All right, and then just one last thing. I mentioned before the MNE library is useful because it includes a bunch of other functions that BrainFlow doesn't have. BrainFlow kind of just has, I'd say, the basic EEG processing functions, but if you need anything complex or you want to sort of, it has a lot of useful like ways to plot the data as well. So it can be useful to use that instead of BrainFlow once you've recorded your data with BrainFlow. So just at the end of the code book here, I've just got the code to, or the line to install MNE, and then we're going to import it. And then to convert your BrainFlow data to MNE format, there's a few things you have to do. You have to get a decent amount of information about the board and the EEG data from BrainFlow. So it needs to know where the EEG channels are. It needs to know the sampling rate, the names of the channels, where the marker channel is, and then also just the channel type. So it needs to know which ones are EEG and which ones are marker channels. Another thing I mentioned earlier is that BrainFlow records data in microvolts. However, the MNE library represents its EEG data in volts. So you have to convert from microvolts to volts. And then you can just specify all this information to MNE and create your MNE object. What I've done here, though, is I've also set what's known as the montage. So if you have a standard EEG headset, like an OpenBCI, which sort of sits on top of your head, each position of a sensor typically gets a different name. And then if you specify this to MNE, then you're able to actually plot out typically like an image of the brain, and you can actually see the values, the EEG values across the brain, whereas BrainFlow doesn't have the capability to do this. So we set our montage, and then we're just going to sort of plot it out. And then the last thing we're going to show with MNE is if you do this raw, which is the MNE object dot plot PSD, we can plot the spectral density graph and see the different frequencies that make up our signal, which is sort of beyond the capabilities of BrainFlow. So we'll just run this and we'll just convert our BrainFlow data into MNE format, and then it prints out the montage. So this is the montage, so it sort of shows the names of all the different EEG sensor positions. And then lastly, it's plotted out I'm trying to think if this is the average like frequencies that make up the EEG signals. So that's usually useful if you're performing machine learning. It's useful to know the frequencies that make up the signal because frequencies that fall within sort of different ranges are associated with different brain functions and activity, and they're usually pretty useful for making any predictions. And I believe that is everything that I had to talk about. So if you have any questions, you can connect with, well, I guess, presenters and other people within natHACKS on the natHACKS Discord, which is, the link is nathacks.ca/discord. And then you can also sign up for the newsletter and follow NeurAlbertaTech on the various different social medias. If you follow this QR code, it should link to the natHACKS site with all the different social media that you can follow Nat on. So yeah, thanks for listening.